Okay, good morning everyone. I hope I'm audible. Okay. Can you all hear me? Okay, great. First of all, I apologize for the last few days we were not able to have class. I was suffering from an ear infection, which was very painful, and thus we had to postpone a few of our classes. But rest assured, within this week, within 4 lectures, in fact, we would finish our course. And uh, with that in mind, let me quickly summarize what we have done so far and where do we stand. Okay. So we started with looking at an introduction of data science, talking about the different aspects of data science, what it covered, what it did not cover, why is it important for us now to study data science, given the present job market and trends and estimating future potential. We saw that data science was a very promising career to choose. Within our data science, we also found that learning some kind of programming language would be to our advantage. And within that sense, we looked at Python and we saw why Python is so famous, especially for in the field of data science. We started looking at different programming aspects of Python. How do we deal with functions and loops, data types, and so on. Later, we moved on to looking at some packages, and those packages are very key to our use of those data science concepts for machine learning and so on. We looked at the following packages. We looked at NumPy, at Pandas, at Matplotlib, Seaborn, and finally, while doing machine learning, we also saw at scikit-learn. Then we went ahead and we said under supervised machine learning, there are two main categories of machine learning. One is for classification algorithms, the other is for regression algorithms. And within classification algorithms, we saw algorithms like KNN, decision trees, random forest, naive Bayes, and so on. And we implemented uh, our example for Titanic dataset, for which we had done something called as data pre-processing. And we had sessions on data pre-processing as well. We prepared our data and we trained our data using these machine learning algorithms. And we also practiced it on one more data set, I think the heart disease prediction data set. And we saw how it worked out. Then we continued our discussion into linear regression. And within linear regression, we saw what is the hypothesis function, how does our cost function look like. We looked at an algorithm called as gradient descent and some of the vectorization of those terms. Now, since in the last class, I was not able to use my iPad, many of those equations I had to just state it out without talking about it. So I thought today it would be a good exercise to both revise linear regression and if we have missed out certain parts to go through them. I think this should finish off pretty fast and then we can move on to demonstrating how linear regression works in practice. Okay. So let me go ahead and let me talk about linear regression. So linear regression or regression is the fact of basically predicting a real value. So in classification, we are predicting discrete values like 0, 1, or survived, not survived, having heart disease, not having heart disease, type 0 of flower, type 1 of flower, type 2 of flower. These are discrete classes. Whereas in regression, we are going for something called as continuous classes, or we have a real number to predict. And for this, our basic model looks like this. So this is the linear regression model, which says that my output y hat is equal to theta 0 plus theta 1 times x1, theta 2 times x2, and theta d times xd. These different terms x1, x2, xd are different dimensions of data, whereas the weights here, theta 1, theta 2, theta 3, theta d, are the weights that are associated with these terms. So here it says how much important is x1. So x1 is as important as the weight theta 1. Okay, if theta 1 is having a higher magnitude, that means x1 is having a higher magnitude. If theta 2 is negative, theta 1 is negative, then x1 is associated negatively or correlated negatively with the output variable y, and so on. We also saw that there's a bias term called as theta 0, and we can combine all of this equation into this summation form of theta j xj, where j goes from 0 to d, with the assumption that x0 is equal to 1. So we are assuming when we are writing this that x0 is equal to 1. We also saw the cost function, which is the relation of how good or how bad our model is doing with respect to the output variable. So if we look at this example, we see these dots, and these dots are different data points for different values of x. So when x is this value, this dot represents what is the y value here. And if we estimate or we model this using this line, we can see how good or bad this line is by looking at our error terms. So error is how far is our line from the actual prediction. So this distance is our error term. To know how good our entire model is, we cannot just look at one data point. We have to look at all the different data points. So when we take all the different data points, take these individual error terms, square them up. The reason for squaring is we don't want to differentiate between a positive error and a negative error. We don't want these errors to cancel out. Okay? So when you give a square, we can add all of these errors. And the aim of our machine learning algorithm, here linear regression, is to minimize this error. So minimize this error. This error can be mathematically stated as this, where we say this is our hypothesis minus the actual value, which is our error, square of the error, sum of all of these errors, and average it by 1 by 2. And we have an additional term of 1 by 2. This will become evident when we look at our gradient descent algorithm. Okay. Here I'm just giving different intuitions of how different lines will look at. So if we look at a line like this, my error would be 0. If we look at a line like this, I would have some positive value of error, some positive value of error, some value of error. Similarly, if we look at lines this side, we would say that our error would look like this, and we could link our cost by this graph. And what this graph basically suggests is when I am at the right value of my theta, when I am at the right value of my estimate of the model, then we have the best model. When we have the best model, my error is 0. But whenever I go less or higher values of theta, which are not right, I end up with different lines. And these lines are not good models. That can be seen as the height here. That is the cost that I see here goes on keeping up. So instead of finding out the right value here, we could imagine minimizing the cost would also give us the best option. So that is just the intuition for relation between our data, our model, and our cost. Going ahead, we can see if we have 2 dimensions of data, then our cost does not look like just one curve. In fact, it looks like a surface. Okay, and this surface has a 3-dimensional surface where your x and y dimension represent theta 0 and theta 1, whereas the z dimension represents the cost. And the aim here is also the same. We need to find what is the minimum cost. Okay, so we'll imagine that in the next slide. The formula remains same. Here, when we look at different intuitions, we are looking at how different models. So here we have these dots or these crosses that represent our data. And if you want to fit this data with a curve, we want to see how good that curve is doing on this 2-dimensional plane. So the same graph here is represented as contour plots here. In contour plots, each of these ellipses represents the same cost. Okay. So here in the last, these brown lines represent the same cost. As we go on making smaller and smaller ellipse, the smallest ellipse is basically the ellipse that has the least amount of cost. And our hope is that we want to, let's say this dot here represents this model. And our hope is how can we come from this dot to this dot and see how this model becomes better. Okay. So this is slide 1. And slide 2, we are moving from here to a point here, closer to the minima here. And as we are moving closer to the minima, we can see our model has changed from this to this, which is not as good, but a better model than before. As we keep going ahead, we can see Once we reach the minimum point, we have the best model. In fact, this is a different way of seeing the same problem where we are trying to fit our model to this data, and we are doing this via the proxy of the cost. As we reduce our cost, as the cost becomes lower and lower, we can see that we'll get a better and better model for our data. And this can be imagined like this. So we have a basic search procedure. That is, we have a point and we are trying to travel to the minimum value here. The only way we can do that is by taking a steep curve downwards. Okay. So every time we move downwards direction, we will end up into this minima if we start from any random point. Okay. And for this, we had discussed something called as gradient descent. The algorithm gradient descent helps us to change the values of our weights. So if you look at here, the strategy of gradient descent is this. We will start with an initial theta. So we initialize theta randomly. So let's imagine we have a three-dimensional problem. So three-dimensional problem means I have three input values, x1, x1, x2, and x3. And corresponding to each of these three inputs, I have three weights, theta 1, theta 2, theta 3, and a bias weight theta 0, which makes our hypothesis function something like this. Okay, I'll write it here. So our output y is equal to theta 0 plus theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3. So this is our hypothesis function. And to make this hypothesis function, there are four unknown values. Okay? Theta 0, theta 1, theta 2, theta 3 are four unknown values which we are trying to search. So our algorithm says start with random values. So we start with random values. Now, if we start with random values, we need a way of updating these random values so that these values of theta come to the right value of theta so that our model fits best. So we have one strategy. We'll say that we will update the value of theta by this formula. We'll take the old value of theta and subtract this term from it. So this term can be divided in two parts. We have one, which is the learning rate, or which is the rate at which we will learn. The second is the gradient, okay, which gives the algorithm its name, gradient descent. Okay, so we'll say the new value of weights, the new values of thetas, our old value of thetas minus the learning rate multiplied by the gradient. What is this gradient? So let us look at this graph. In this graph, our hope is that this is the value of the cost function. This is some random theta that we started with. Now we want to move this theta here. So this theta somewhere near 1.25 is the right value of theta because it gives us the least cost. So when we start with this, how do I move to this point? So we say, let us find out the gradient at this point. The gradient at this point gives us the slope. If we move in the negative direction of that slope, then we will get closer and closer to this point. So we take the negative direction, we move and distance alpha, we come to a new point. Then we say this is our new value of theta. Let's take a slope here, move to the next point. Let's take a slope here, move to the next point, slope here, move to the next point. And what will end up happening is, as we are moving to these next points, we will settle down somewhere here, which is the valley point. Okay. So our gradient helps us provide the slope that gives us the direction in which we should move. Okay. Now here, since we have four values of theta, we need a way of updating all of these four values. So we start by writing these equations. We say to update this value of theta 0, we'll take the old value of theta 0 minus alpha times the difference or the derivative of the cost with respect to only theta 0. Then in the next one, we require the same equation with respect to the cost with only theta 1. Okay. So what we need is, we need the derivative of the cost with respect to the corresponding values of theta. There should be one more equation here for the fourth value, which is theta 3 is equal to theta 3 minus alpha times partial derivative of j of theta 3, partial derivative of j of theta with respect to theta 3. Once we evaluate these gradients, then we can update this value of thetas. The question is, how do we evaluate these gradients? Which is how we will solve this part. So we'll say, okay, this gradient evaluation can be done by knowing what is the value of j theta. So we saw that the value of j theta comes out to be this equation, which is 1 by 2n. So this 2 I have not yet explained, but 1 by n is averaging out the terms, summing of our cost over all these examples. That is our hypothesis minus our actual answer. That is our error, square of our errors, sum of our errors over all examples, and averaging it over 1 by n. That gives us our cost. Now, the derivative of this cost is very easily can be found out. Let's look at that term. So we say, okay, derivative of that is partial derivative with respect to theta j. Here we have just expanded this term. Instead of h theta of xi, we have expanded this to our summation theta j xj from j going from 0 to d. Okay, so this is this expansion. Now, when we have to take partial derivative of this entire term, we can take this partial derivative inside this term. So we say, okay, let me take 1 by 2n and summation over all these samples outside. Let me take the partial derivative inside here, and I will try to evaluate the partial derivative of this term. And that is okay. So here, if I have one term, its square, its partial derivative will be 2 times that same term, and chain derivative or chain multiplication gives us the idea that we then have to take the derivative of this internal term. So we take this 2 comes here, we get the same power minus 1, which is just raised to 1, and then the partial derivative of this internal term. Okay. So we are very close to our answer. This one part, we can see in this part, this 2 and this 2 gets cancelled. So the initial purpose of putting this by 2 in the cost was that once we take the derivative here, these 2 will get cancelled and our ultimate equation will be a bit simpler. If we look at this term now, we are trying to say we have to find the partial derivative of this summation and y with respect to this theta j. Now, if you look at this y, since this y does not have any term of theta j, we can simply cancel this out. We are left with only this summation with respect to derivative with respect to theta j. So this can be understood by looking at this part here. We take the expansion of this summation of theta j xj. So it gives us theta 0 x0 I, theta 1 x1 I, theta j xj I, theta d xdi, and multiple terms in between. So what partial derivative says is only theta j is the variable. Everything else becomes a constant. So the derivative of this first term with respect to theta j becomes 0. This becomes 0. This becomes 0. So every other term becomes 0 except for this term, which has theta j in its form. And derivative of this theta j becomes 1. We are left with only this variable, which is xj of I. So this xj of I is what we end up here. And when we put that in terms of k or j, we see that this is the term that ends up here. So now this is our evaluation of our partial derivative of the cost with respect to a particular value of theta j. Okay, or you could say theta k. Okay. Both are like here I mistaken started with j, but I ended up formulating the answer in k. This should actually be j. So we end up with our cost function, which says 1 by n because of all the samples that we have, summation over all these samples of this term. This term is summation over j of theta j xji minus yi multiplied with xji. Once we have that, we can then replace this into our direct formula, which says that theta j, the new value of theta j, is the old value of theta j minus the learning rate multiplied by this term, which is average summation over all terms, summation over all dimensions of theta j xj minus y multiplied by xj. Going ahead, what is the stopping criteria? So we have to repeat this until convergence. Our convergence generally is this. If I take the new value of theta and old value of theta, and I take its L2 norm. So L2 norm is taking the square root of the sum of all of the squares of these individual terms. And if that is less than some low value, epsilon, So we can keep different values. If I keep 1e minus 3, that says that if all of my thetas are not changing by this small value, then I have reached convergence. That is, I have reached to the bottom of that curve. Okay, that is my stopping criteria. We also saw how alpha plays a role. So alpha chooses how fast or how slow we reach this point. If we say alpha is too small, we will take multiple iterations to reach to the endpoint. And if alpha is too large, we will instead of converging down, we will actually be diverging. So it is very important how we choose alpha. And when we will go to our example just now, we will see that alpha plays a big role in whether our model will work or not work. Finally, we also went and we saw some ways of doing vectorization. That is, writing the same formulas into a form which allows us to code it better, and not just code it better. It gives us an easy, compact way and faster code by doing vectorization. Okay, so we just saw that this term, that is summation of theta j xj going from j is equal to 0 to d, can in fact be written as this. That is x transpose of theta, x transpose multiplied by theta, or theta transpose multiplied by x. Okay, that is the vectorized form of this summation function. We also saw that we can extrapolate this idea of summation over one sample to summation over all samples in fact. That is, if I take my individual examples and write them as rows here, then taking those individual examples, writing them as rows and multiplying them with theta, just by doing something like x and theta, gives me our entire cost for all of the samples. Okay, so this is so simple. Just by doing this matrix multiplication, you can take your initial value of theta, that is the weights that represent your model, and evaluate this model for all of the values of samples that we have. Okay, so instead of doing this n different times, we can do it just by this one equation. So vectorizing it actually saves us a lot of time. Going ahead, we can also vectorize our cost function. And here I've shown how this looks like. So if we look at our cost function, we can evaluate our cost function by saying that this term comes out to be this summation, and this summation comes out to be x times theta, which we had seen in the last slide. Okay. And now just evaluation of this term, we can say instead of taking the square of this, we can divide this into two parts. That is x theta minus y as one matrix of one row and n columns, and its transpose multiplied by x theta minus y, which is n rows and one column. So just this matrix multiplication. So this term evaluated once, do matrix multiplication and divide it by 1 by 2n, and we get our entire cost. Okay. So again, factorizing this also has saved us a lot of time in terms of cost. So this is a quick summary of what we had done in the last class. Also, probably I hope this helps you understand this better. What we can do next now is implement this linear regression code in our Python and see how this works. So let me shift my screen to my laptop. Okay, so I hope you can see my screen, and let me put the chat window on top. Okay. Okay, great. So with this, we can start looking. Let me zoom this a little better. Okay, so we'll first load our data. So we'll use the very famous Boston dataset. So Boston dataset is a house pricing dataset that is a very common example for learning linear regression. So today we'll not focus too much on the data. We are more interested in implementing linear regression. And once we have done that, in the next class, when we go to our more advanced example on linear regression, we will focus more on data rather than the algorithm. Okay. So here I first load NumPy for all our mathematical stuff. So we want to do linear algebra, we want to do calculus. So NumPy is a must. We take our data set, the load Boston, from scikit-learn's dataset series, and we take matplotlib so that we can plot our learning function. First thing, we will load our data. So here I load the data into the variable dataset. If I just look at the variable dataset, you can see that it contains a lot of stuff. So primarily we have dataset as a dictionary, and the first element here is the key called as data, and we've got values here that represent our data. Then we have the target variable, and we have all of this as a target. We have feature names that describe what are the data, and what are the names. So serium, Z, and index. Right now we'll not focus on this. And then we've got some description of the data. So let's quickly print the description and see if we get quick insights on what this is. So I go zip VSCR and I'll print this. So this gives us a quick summary of our data. So our data has 506 different data points. There are 13 attributes. These attributes are given here, serium, Zn, and those are short forms. The full forms of the attributes are given here. There are no missing attributes. This data was collected by, the creator of this data was Harrison D and Rubenfeld DL. You can get this data from this link, and that's it. Okay. And now let's load the data part. So we will load the data part into the variable X, which is our standard variable for our input features. And we will load our answer, that is our target, into the variable Y, which is our target variable. And when we execute this, we can see that there are 506 examples as shown here. We can print the shape of our data, X. We can see that there is 506 rows and 13 columns. And let me print some parts of X. So let me print X, maybe the first 5 rows, all columns. That gives you some sense of what this data looks like. So this is one row of data. One row of data has 13 columns. So this is, our first value is 6.32 e raised to minus 3, that is 0.006.32. We have some small values, we have some large values. This is what our data looks like. And like this, we're looking at 5 rows of our data. All of our rows, there are total 506 rows. Okay, let me cancel this. Let me quickly, since we are going to implement this, I have written down the important functions here. So there are 4 important functions that we need to implement: hypothesis, cost function, gradient descent update, and convergence. So our hypothesis looks like this: h theta is theta 0 plus theta 1 x1 and so on, which can be evaluated by the summation. Or as we saw in the last part, we can vectorize this as x times theta. We can look at our next equation, which is the cost function, and the cost function can be evaluated like this, or in a vectorized form, it can be evaluated by 1 by 2n, x times theta minus y raised to, that is transpose of that, multiplied by x theta minus y. A gradient descent update comes to this. So this is our answer. So once we had evaluated the derivative of j theta with respect to theta j, we found that it comes to be this expansion. So we say theta j is equal to theta j minus alpha times 1 by n summation of h theta xi, that is our hypothesis, minus the answer multiplied by this. We can also take this equation and we can vectorize it in this form. So vectorizing it here becomes alpha times 1 by n times x transpose multiplied by x theta minus y. So again, this makes our job very simple. So we don't have to implement this loop. We can directly write this equation and that will solve our problem. This is our criteria for convergence. And this criteria for convergence is L2 norm, and L2 norm is given by this equation. So this is a quick cheat sheet of the formulas that we'll be using. So let us start with doing some feature standardization. That is, we see all of these features belong to different ranges. If they belong to different ranges, then our gradient descent will not work better, or it will take a lot of oscillations. So when we do something called as feature normalization or feature standardization, we convert them into the same range. And in the same range, our gradient descent will work best. Okay. So if we look at the feature names, we see dataset.feature names. These are the names of our features. Let us put the data into a data frame, pandas data frame, so we can view it nicely. So I import pandas and I create a data frame using X, and our column names are given by dataset.feature names. If we run this, you can see this is what our data set looks like. So there are 13 columns and 506 rows, and this is what our data is. Okay. If we do a describe on our data, we can see min max and we can see standard statistics for all of our data points. We can see serum has a maximum of 88 and a minimum of 0.006. Zn has maximum of 100, minimum of 0. And we can see different data points have different ranges. So there are quite a big range, right? From uh, CHAS, which has a maximum of 1, to tax, which has a maximum of 711. So there's a huge range in between. That means definitely we have to do some standardization. So we'll do that by this. We will take our total length of samples into the variable n samples. If you remember our standardization formula is the input minus the mean divided by the standard deviation. Okay, so when we do that, subtract the value from mean and divide it by standard deviation, we have the final distribution as zero mean and unit deviation, standard deviation of 1. So we will require mean and sigma. So let us evaluate that. So np.mean, so numpy helps us evaluate the mean very easily. So mean of all the rows, mean. Okay, so sorry for the delay. I just have to forward a mail to my boss. I'll do that parallelly. Let me continue here. So here we have evaluated all the mean for our 13 rows and all the standard deviation for the 13 rows, and we can see they are quite a bit of range, right? And to standardize it, we can simply do this. Our new value of x is equal to old value of x minus mu, that is our mean, divided by our sigma. So when we do that, sorry, I have to run this first. If we do that, and then now when we see the mean and sigma of a new distribution, we can see that the mean and sigma for all of our distribution looks like 0 and 1. Okay, so 0 mean for all the rows and 1 standard deviation for all the columns as well. Okay. And this is how our new data, that is our processed data, looks like. It has the same shape as before. Okay. Just give me a moment. Okay. Okay. So we have our uh, 13 rows, 13 columns, and 506 rows. In the next part, we are doing an H stack. So if you remember from our previous classes, an H stack is basically a horizontal stack, and we are doing a horizontal stack between these ones and this X that we have preprocessed here. Can any of you tell me what is the purpose of adding this ones to this additional data that we have? What we are in fact doing is we have 13 columns, and now after doing this, we'll have 14 columns, where our first column is having these ones. Okay, any idea why we are doing this? Okay, since I'm not getting any answers, either the idea was not clear, or maybe it is too difficult to type. Let me tell you what the answer is. So adding this ones, if you remember, these ones are that value of x that will be multiplied with theta 0. And theta 0 is our bias term or our base term. And this 1 multiplied by theta 0 helps us to formulate our equation into an easier form. Okay, so we can write this as a summation, and thereby the summation can be written as a matrix multiplication and so on. Okay, so we add this once. Oh, now I have added this 2 times. So I have to then please just 1 second. So let me make an error here. Restart. Okay. Sorry. Uh, I was having a series of conversations with my boss. All right. Okay. So we have executed this so far, and these are our data points: 506 rows and 14 columns. So 13 that come from our data, and the one additional column, it comes because this one that we have attached here. Let us then, since we have our data ready, let us then create some basic functions that we will use for our linear regression implementation. So we'll use a function called as compute cost, which is the implementation of this cost. So I've done it in multiple ways. In this first way, I'm using just summation np.sum. That is, you could imagine that this is uh, not using vectorization. So part of it is using vectorization, and part of it is just using the np.sum function. And here, if we time this, we can see how long does it take. So it takes 22 microseconds to run this. But once we vectorize this part also, so this part instead of np.sum, we vectorize it using uh, our matrix forms. Then we evaluate it, and now when we look at the cost, we can see that it takes, let's give it a few more seconds. Okay, so it takes 13.8 microseconds to evaluate this, which is roughly half the time that it took us for doing this step. Okay, and even in this step, we have actually used some vectorizations. Okay, so we can see that using vectorization not only makes it simple for us to implement, but also saves us a lot of time. Going ahead, we are looking at the gradient descent function. So this is the function that we'll be using for evaluating the gradient descent. We can see that the new value of theta is old value of theta minus alpha times 1 by n x transpose multiplied by x theta minus y. So here, this is what our loop will come out to be. We are saying for n number of iterations, for the number of iterations given by the input, we will update our parameters. That is, we'll update our theta by this formula. So we'll say the new value of parameters is old value of parameters minus learning rate by number of samples multiplied by x transpose multiplied by x times parameter. So x times theta minus y. Okay. So this is our summation. This is our update. And after updating, at every update, we will also store the value of the cost. Okay. And this will help us to see how our cost is reducing. So let me execute this. So this is our function. Now, when we go to this implementation, let's start with 50 number of iterations with a learning rate of 0.1. And we will see the number of features, and we'll create our initial parameters. Okay. So these are our initial parameters, which we started with all zeros. We will compute the cost for these parameters. So when all of our parameters 0, our cost comes out to be 296. Okay, and our hope is that as we are training these parameters, our cost will keep on reducing. Okay. Now we will also see what is our compute cost in the vectorized term, and that also gives us the exactly same answer. We will use this because this is faster. This is the value of our features. That is, these are our weights. we start with all values of 0. Let's start with all randomized values. So if we start with all randomized values, these are our randomized weights. And this is our implementation of gradient descent. So we'll go with 50 iterations. Let me put that 50 here, with 0.01 as our learning rate, our number of features here, so and our parameters as random values of parameters. We will first find the initial cost. We'll print the initial cost. Then we'll go to gradient descent. And after gradient descent, we will print the optimal parameters and we'll print the optimal cost. Okay. So let me execute this. And now we see very interestingly what has happened. Okay. So we started with an initial cost of 309. And after going 50 iterations with a learning rate of 0.01, we can see that these are our final parameters, theta 0, theta 1, theta 2, theta 3, and so on. And this is our final cost. Okay, so now the cost has reduced, but it is not reduced so much. Let me take a better example. Let me take a learning rate of 0.1 and execute this. We can see that our cost has now significantly reduced. We started with some random cost of around 264 and we ended up with 11. Since we want to have reproducible results, let us initialize our parameters with just zeros and not random, so that at least for now we can see how it matters. And here we can see we start with an initial cost of 296 and end up with 11.33 Sep cost, which means that our model is now pretty much trained. Let us view how our cost function is changing. Okay. So here, since we stored our cost function in gradient descent, we can get that cost function in J history, and we can plot that J history using matplotlib's line plot. And when we do that, we can see that this is our cost. We started with a high cost of 296, and over multiple iterations, we have reduced our cost to somewhere near 30 or 40 iterations. We have reduced our cost to 11, and we can see our cost does not go any further down. That means that we have actually trained our model, and these weights, they represent to us our final answers. Okay. Let us now play around with this area. Let us now play around with this a little bit more by changing these weights and these iterations and learning gradient. Okay, so let me ask you probably a few questions. What will happen if I reduce the value of alpha? Okay, if I reduce the value of alpha, right now alpha is 0.01. You have seen what happens. If we reduce the value of alpha, it takes longer to train. So let me take 0.01, and we can see that we have reached only 109. And if I go here, I can see that our cost is reducing, but it has not reduced so far. Even after 50 iterations, we have not got to our answer. So we need to increase the number of iterations. Let us increase the number of iterations, let's say 500. Let's try. And we can see with 500 iterations, our model maybe around near 300 iterations, it was able to find. So a lower value of alpha takes us much longer. So if you remember with alpha of 0.01, we were training around in 30 iterations, whereas now it took us 10 times longer in 300 iterations. Let us see what happens if we increase the value of alpha. So let us go first to 0.1 again. With 0.1, we have within 30 iterations. Let's now increase it to maybe 0.2. And after 0.2, we can see the cost is 11. So it has trained fine. And it has given us our answer in probably 10 to 15 iterations. We have our answer. What happens if we increase our learning rate more? Instead of 0.2, if we go to 0.3, let us see now. We can see even 0.3, it has trained. It has given us an answer in maybe 10 iterations. What happens if we go further? Let me go to further and let me show less number of iterations so we can see the plot better. We go with 0.4, with 0.4, it does not train. Okay, you see after 0.4, we have this as our cost. So we can see our cost started with a lesser value and our cost increased further. In fact, when we look at the cost, we can see our cost is going on increasing. That means 0.4 is not serving our answer. Point 3 is serving our answer, where we are reducing our answer, reducing our cost down to a lower number. But with point 4, we are not tuning. It takes us longer to, it diverges, the solution diverges. All of these simple ideas, we have written smaller functions, but a more standard way of doing this is by converting those functions into a class, which we can use any other. So here we start with we create a class called as linear regression. We have the init function, which is the constructor, and we initialize all our basic values like alpha, which is a learning rate, number of iterations, number of samples, and so on. Okay. So here we have our initializations. Then we call the fit function, which is our gradient descent implementation, which is going through multiple loops, and here we are training the parameters. Our score function, which helps us to see what is our evaluation. So this is just implementation of our cost, and this gives us how good or how bad our model is doing. Finally, we call the predict function that will help us to predict for unknown cases. Now, what we can do is we can compare our implementation with scikit-learn's inbuilt implementation. So I am taking the same data set as before, taking our, importing our model, importing scikit-learn's model, and we'll test how good or how bad our data is doing. So we take the entire data set, divide that into train and test using the train test split method, which divides the test set as 30% and train set as 70%. We take our regressor and fit our model. We take scikit-learn's model and fit that model. Then we call our accuracy to find out what is our training accuracy and scikit-learn's training accuracy. And we compare our test accuracy with scikit-learn's test accuracy and put that into a data frame. So when we execute this, very interestingly, we can see our implementation gave us almost the same training accuracy as scikit-learn's implementation, and our implementation gave us a little bit less accuracy than our test system. Basically, scikit-learn's implementation may have many more things, including regularization and other stuff, which we have not included in our model. And if we include those, probably our model will also become as good as scikit-learn. But this goes to reveal that if we are doing the math right, then our models will give us similar or better answers depending upon how we implement it. Finally, let's look at X test, Y test. That is for our test data set. This is our input, and this is what our model actually wants, and our prediction is what we are predicting. Okay, so here we have the actual answer that is required, our model's prediction, and scikit-learn's prediction. And when we put that into a row, we can see how good or bad we are doing, right? So the actual answer is 23. Our prediction is 28.66, and scikit-learn's prediction is 28.65. If we look at multiple places, so we see that we are not very close, but that is the best we can do with linear regression. Okay, so we have in many of these cases, you see that we're actually not that far. So here 17, our model scikit-learn, both of us, we predicted 17.37, very close to our data. Even here 14, we are predicting 14.11 and 14.08. Okay. So with this, we have implemented linear regression. Linear regression is basically when we are trying to use machine learning to predict our real valued class, and we saw how to implement it from scratch. We went through all the math behind it. We also saw how to use scikit-learn's models to implement this. In the next class, what we'll do is we'll go to a more realistic data set. So we'll look at the same data set, actually, the Boston housing pricing data set. But here we did not focus on what this data is representing and so on. In the next class, we'll focus on that. We will look at how the data set is distributed. How do we do data pre-processing for the data set? What are the different columns? If there are missing values, how do we populate those missing values and so on? And then we can implement a linear regression. Okay. So with that, we can stop for today. Thank you everyone for joining. We'll meet you tomorrow. I'll stop sharing. Okay, Neerja ma'am, I will exit for today. Okay, bye-bye. Have a good day.